Hello, and welcome to the second part of the piecemeal functions. Today we're going to look at how to sketch the function fx, given that it's broken into these three piecemeal functions. So remember, a piecemeal function is made up of multiple components, and they have separate domains which specify where that particular function exists. So in order to sketch a piecemeal function, what you want to do is to draw the graph separately over the correlating domain and then combine them all together. So I'm going to start off by drawing a big axis or plane. And we'll start off with the first graph. So the first graph is y is equal to 2x minus 4 for x is greater than or equal to 1. So this is a function because it has a graph, an equation, and it specifies which part of the graph we are drawing. We're drawing for values only for x is greater than or equal to 1. So you can first start off by drawing the entire graph. So we start off by finding the y-intercept. That, of course, is just minus 4. And we find that by setting x equals 0. Then you find the x-intercept. So the x-intercept is x equals to 2. And that's found by setting y equals to 0. So what your graph will look like is something like this. If I plot in x is minus 4 here, sorry, y is minus 4, and x is 2 could be essentially somewhere here, I'll draw a very light line through these 2 points. Okay, a very light line like that. Now, I'm only concerned about the values for x greater than 1. I don't need the entire graph or the entire line. So x equals to 1 is somewhere here. Right? Let's say that this is 1. So I only care about values of x to the right of 1. Hence, the only parts which I really need is anything from this point onwards. Like that. Okay, I wouldn't recommend shading a line like this in a test. Just rub out the line, the section that you don't need. Okay, like that. I'm just shading darker to show you that this is the part of the graph that I keep. Okay, so that's the first graph. Now let's go down a little bit so we have a bit more space. The second graph is the equation y is equal to x minus 3. Just one thing to note, I'm using y, but you could write fx instead of y. It's okay. It's just that so that I can write y-intercept and x-intercept to be more consistent. So the y-intercept for this case would of course be minus 3. Same idea when x is 0. And the x-intercept occurs when y equals to 0, and that is when x is 3. Okay, and this is for the function x minus 3 for values of x greater than or less, greater than minus 1 and less than 1. Okay, so that's the domain that we are drawing the graph around. Now, one thing to note is you can see that in this domain it doesn't include 1. Okay, see, it's just less than 1. But there is a possibility that the graph is connected to the previous graph. So this y equals to x minus 3 could potentially be a continuation from y equals to 2x minus 4. So what I mean by that is, at the point of x equals to 1, this point here, we could see the graph being continuous at that point. So drawing something that connects the red graph, y equals to x minus 3, to the green graph. Now we have to check for that because not all graphs are continuous at the point where they end. So in order to check for that, I first need to see for the green graph, y equals to 2x minus 4. I got the colors mixed around. So what I might do is I might circle or box the first graph in red because I've drawn the graph in red, and I'll box the second graph in green because I will draw that in green. So let's check out what's happening at the point of x equals to 1. For the red graph, at x equals to 1, The y value is 2 lots of 1 minus 4. All I've done is substitute 1 into that equation there. So then y is equal to minus 2. So what that's telling me is that this value is minus 2 at x equals to 1 at that point. Now if I test at x equals to 1 for the green graph, or y equals x minus 3, where would that be? Well, it's going to be y equals to 1 minus 3, which is minus 2. So because both the values are the same, that means that the green graph will start at the same point the red graph ends. Okay, but just remember, this might not always be the case. Okay, not everything will connect all the time, even though we want them to. So minus 2 is here. It's starting here. Okay, so to draw the graph, we've got our y-intercept and our x-intercept. So minus 3 is maybe here. So it's going to pass through this point. And it is going to go up until negative 1. Now I don't really need the x-intercept because I don't think my graph is going to go that far anyway. So not very useful here. But I do want to know where the graph ends. And I do that by subbing in x equals to minus 1. So let's see what happens. At x equals to minus 1, my graph is y is equal to minus 1 minus 3, and therefore y is equal to minus 4. So that's interesting, because that tells me that if this point here is minus 1, then my graph is all the way down here. It will pass through that point. That's where it ends. So it should be a straight line between these 3 points. Now, my graph isn't very accurate, so I'll just try to do what I can. Okay, it's a straight line like that. Okay, passing through minus 3, the value minus 1 and minus 4. Okay, so it connects like that. And that's the second graph done. Now for the last graph, we have not a straight line, but a parabola. Y is equal to minus 4x squared. Now for this one, I might use orange to graph this one. So the standard parabola, or this parabola, looks like this. It's a concave down, and the 4 coefficient just makes it a little bit steeper. So it's going to look something like that. Now again, I have to test to see if it joins up with the previous graph. So does it join up with the green graph at all? And in order to do that, I determine what the endpoint is for the green graph. The endpoint is here, remember? So that's where we left off. So at x equals to minus 1, what is my parabola doing, or where is it? That'll be y is equal to minus 4, minus 1 squared, and that means y is equal to minus 4. Okay, so that means I've got, the green graph was at y equals to minus 4 before, and the parabola starts at y equals to minus 4. So what does that mean? It means that it does start at that endpoint, hence it connects. So what is that going to look like? Well, if you have a look at the parabola, you can see that it just goes down like that, right? There's no sort of intercepts that we need to worry about because the intercept's over here at x equals to 0. So in order to finish off this graph, it's just going to be a line that goes down like that, okay? A curve. Sorry, not a line, a curve that goes down like a parabola. And that is essentially how you would sketch your piecemeal function, made up of 3 separate graphs and 3 separate sort of domains in which we draw those graphs. Okay, and it goes down forever, and that is the function of fx. So I'll just quickly label that, and that's it. Okay. All this extra working out here, the blue ones, are very important because they tell you whether or not the curve is continuous or the function is continuous at those points, at the critical points, we can call them, the points where the graphs sort of start and end. Okay, sometimes you might have graphs which go something like this. You might have a graph here, and then all of a sudden it might pick up maybe somewhere here. Okay, that is very possible, and this is what we call a non-continuous graph because there's sort of like a jump at this particular value here. Okay, so we hope for nice graphs like this, but we don't get them all the time. All right.